Okay. Hi, everyone. I'm Yanlai Yang from New York University, and today I'll present Memory Storyboard leveraging temporal segmentation for streaming self-supervised learning from egocentric videos. This is joint work with my advisor, Professor Mengye Ren. So continual learning methods in computer vision predominantly benchmark on static and curated image datasets like CFAR and ImageNet. But these images are not likely what an embodied lifelong agent will actually see in real-world environments. Say we deploy a robot to a new environment and let it freely interact with the environment. This is the kind of data that it will see, a continuous, uncurated, egocentric video stream. And we want the robot as a lifelong learning agent to be able to continuously adapt the visual representations from its own egocentric video feed without any human curation. We refer to this problem setting of learning through streaming video experiences as streaming self-supervised learning, and it is what we try to study in this paper. For people who are unfamiliar with self-supervised learning in computer vision, the goal is to learn a visual representation of images from a large amount of data and then transfer the learned representations to a downstream task. For example, shown here is the popular SimClear method, which maximizes the similarity of representation of two different augmentations of the same image and minimizes that of different images. Self-supervised learning methods has made many achievements in recent years in computer vision. However, when we apply them to naturalistic videos, they turned out to work very poorly. This is mainly due to the non-stationary distribution of visual features and the high temporal correlation of images in the stream. In this work, we aim to explore mechanisms that enable efficient learning of visual representations and concepts from streaming video. Let's get into a bit more detail of the problem setup. So we are given a never-ending egocentric video stream with frames x0, x1, and so on. And our goal is to learn visual representations completely from scratch from the stream. Every step, the model sees a new batch of images. For example, step 0, the model sees images 0 to 3, step 1, 4 to 7, and so on. And we assume a one-pass setting. So the model will have to discard most of the frames it sees in each batch and only keep a relatively small replay memory, M, with fixed size. Every step, it can add the newly seen images to the buffer and retrieve some images from the buffer for training. One relevant problem setting that was previously studied is continual self-supervised learning, also known as unsupervised continual learning. In continuous self-supervised learning, we have a sequence of tasks, and we do multiple epochs of training on each task. In our streaming video self-supervised learning, instead, there's no explicit notion of task, and we do a single pass instead of multiple epochs. And another important difference is that we focus on egocentric video data rather than curated image datasets. In naturalistic videos, the distribution shift directly follows from the video scene transitions. And we argue that it better models the naturalistic scene transitions in real-world data compared to the static image benchmarks. And video data also involves high temporal correlation, which makes it challenging to directly apply self-supervised learning algorithms on it. But this also means that we can exploit the temporal structure within the video data and group nearby similar frames together to learn representations. This leads to our key insight of learning good representations from scratch on a video stream, which is to leverage what we call event segmentations. Event segmentation is actually a mechanism in human brains that we use every day. Take your recent vacation trip as an example. Instead of having individual memories here and there, you'll probably group these memories into events and activities with temporal boundaries, like exploring a city in the morning, dining at a restaurant at lunch, and relaxing at a beach in the afternoon. So event segmentation refers to the mechanism where we spontaneously segment visual streams into hierarchically structured events and identify the event boundaries. We can apply event segmentation to learning from streaming videos. For example, here we show a storyboard of images that the model may encounter in an egocentric video stream. We can identify separate events and activities like reading a book and playing with Lego blocks from this video stream, and contrast between these temporal segments to learn good representations. So how do we get these temporal segments from a video? We use a quite simple optimization objective, which is to maximize the average similarity within each temporal segment. Here, the T1, T2, all the way to Tn-1 are the boundaries of the temporal segments. And we assume that the number of temporal classes n is predetermined. And we use a greedy approach to approximate this optimization problem. Here is a visualization of what the temporal segments we got look like. We can see that it can successfully identify the boundaries of different event segments, like playing with an iPad or sitting on a sofa. Okay, so we are able to generate temporal segments from a raw video stream. Now we introduce our main contribution, the memory storyboard framework for streaming self-supervised learning. Memory storyboard uses temporal segmentation to group the frames into semantically meaningful temporal segments. We then take the samples with the same temporal class label in a batch as positives and contrast them from the remainder of the batch. And we refer to this as the temporal contrastive learning objective. These temporal segments effectively facilitate representation learning in streaming videos. Our final training objective is composed of this temporal contrastive loss and a standard self-supervised learning loss, such as SimClear or SimSciUp. One challenge of applying temporal segmentation in our setting is that it is impractical to apply it on a never-ending video stream. So to accommodate efficient temporal segmentation, we propose a two-tier memory hierarchy. There's a short-term memory and a long-term memory. The short-term memory is a small memory bank that contains most recently seen data. It is subsampled from the raw video stream to reduce redundancy and is updated with a FIFO first in, first out strategy. We only apply the temporal segmentation on the short-term memory to get the event boundaries and the temporal class labels. The long-term memory is a larger memory bank that summarizes past seen data. It is updated with reservoir sampling. The labels in the short-term memory are used to update the temporal class labels in the long-term memory. When a temporal segment is added to the long-term memory, it is merged with existing similar temporal classes based on a similarity threshold. Here is a visualization of some exemplar images in the long-term memory. We can see that this method can group similar visual concepts into the same class. For example, the cyan ones correspond to eating in the dining room, while the green ones is playing in the bedroom. This helps facilitate representation learning. So to summarize, this is our memory structure. We have two buffers, a short-term FIFO buffer and a long-term reservoir buffer. Finally, a training batch consists of samples mixed from both buffers. Now we introduce the experiments. We experimented on two real-world egocentric video data sets, SayCam and KrishnaCam, with a Resident 50 backbone. These data sets feature long egocentric videos taken from the same person over an extended period of time. In terms of downstream tasks, we use linear probing evaluation on ImageNet and iNaturalist datasets for image classification. So here we see an excerpt from both datasets. Yeah, this is an excerpt from the SayCam dataset, which was captured from head cams on babies. And here is an excerpt from the Krishna Camp dataset, which was captured from walking around a college campus. We can see that in these egocentric videos, there is a lot of camera movement and sometimes blurry frames, which makes learning more challenging. In terms of the baselines, we compare to ID training, where all frames are shuffled and uniformly sampled for each batch. We use, in the following set of experiments, we use SEMSIM as the base self-supervised learning method. We also compare to Osiris, which was published at CoLLAs last year. It is an unsupervised continual learning method with a self-supervised learning loss on the current data, a replay loss on past data, and a cross-task consolidation loss. We also compare to temporal classification, which employs a similar temporal contrastive loss as ours, but instead of doing temporal segmentation, it assigns the temporal class labels with fixed intervals. And finally, we consider the minimal redundancy buffer, or MinRed, which adds all the images into a single memory buffer and keeps a set of minimally redundant samples when the budget is reached. Let's look at some results. So here we have 4 colored bars corresponding to 2 pre-training datasets, SECAM and KrishnaCam, and 2 downstream tasks, image classification on ImageNet and iNaturalist datasets. First, we have ID SEMSIM. Then Osiris, it adds 2 additional loss terms to SEMSIM, but fails to outperform ID SEMSIM. Temporal classification, or TC, again, it employs a similar temporal contrastive objective as our method, but you don't use temporal segmentation, and it performs slightly worse. This long mem only refers to if we directly run SEMSIM on the video with a reservoir buffer without any additional mechanisms, it performs very poorly. And MinRed also fails to get very good performance. Finally, our memory storyboard method is the only one that is able to outperform ID SEMSIM by using the 2-tier memory mechanism and adding the temporal contrastive loss. On the other evaluation metrics, we can see that memory storyboard also achieves the best performance. We also explored other very interesting problems relevant to streaming self-supervised learning setting. One particular set of experiments I want to share here is the optimal mixing ratio between the short-term memory and the long-term memory to compose a training batch. And we study how it changes under different memory constraints. In these experiments, we fix the short-term buffer, the size of the short-term buffer to be 5K, and vary the long-term buffer size from 5K to 100K. And we tried different training batch compositions from 12.5% to 75% of the images sampled from the short-term memory. Here are the results for a small reservoir buffer, namely 5K and 10K. And here, each color line represents the performance of different training batch compositions when the model has seen the same amount of data from the stream. So this light blue curve is when we only see 10% of the data, and the purple curve is when we run through the whole data set. Here, we made an assumption that the amount of data we sample from short-term memory in each batch is the same as the number of new images we see from the video in each step, to make sure that each new image is expected to be seen once if it's not added to the long-term memory. So with a larger percentage from the short-term memory, we actually see fewer gradient steps. We can connect some points in the figure to get these black curves. So each black curve here represents the performance of different training batch compositions when the model has taken the same number of gradient steps. We observe that taking more images from the short-term memory gives better results when the memory budget is small, probably because the model is more likely to overfit to the long-term memory in this case. Here we show the results for a larger reservoir buffer, namely 50K and 100K. And we observe that each individual color line is going downwards, especially in the 100K curve, suggesting that we want to take more images from the long-term memory and more gradient steps when controlling the amount of data seen by the model. However, the black curves first go up and then go down, meaning that a balanced buffer is optimal when we control the number of gradient steps taken by the model. Okay, to conclude my presentation, in this work, we propose Memory Storyboard, a framework for self-supervised learning from scratch through streaming video experiences. It focused on a setting where we directly learn from natural, uncurated video streams, and it enables efficient mutual learning of visual representations and event concepts. To create these event concepts, we use temporal segmentation and merging of temporal classes. To enable efficient representation learning, we use a temporal contrastive loss and a standard self-supervised loss as the training objective and a two-tier memory hierarchy. Please refer to our paper for more details. Thank you for your attention.
Thank you for the wonderful talk. I wonder, you mentioned one of the advantage of this work is that it's training from scratch. But then for the segmentation, you also use this similarity on some embedding of the images. So in that case, for your self-supervised part, can you just use these embedding to like as a pre-trained model?
Yeah, thanks for the question. It's a great one. Yeah, it's the details that I didn't put into the presentation. So yeah, as you mentioned, for a random initialized model, the similarity score computed by the model is not too great. Like we observed that the similarity score are very high for any pair of images for a random initialized model. So we combat that with two tricks. So one is that before we start any training, we fill the long-term buffer with the first images we see. So say the long-term buffer it has size 10K, then we don't do any training for the first 10K images because they are just too redundant, and we just use them to pre-fill the buffer before we do any training. The second thing is that we also warm up the model. So for the first, say, 100 epochs, for the first day, there's no epoch, so 100 steps. We only apply the standard self-supervised loss, and we don't do any temporal classification, and we also don't apply the temporal contrastive loss. And only after we learned a reasonably good visual encoder, we start to do this.
Okay, thanks.
Any other questions? Okay, let's thank our speaker.